determined that it was nonpolar because these two are going to cancel one another out, and these two can cancel each other out. It's like, again, we're canceling out those partial positive and partial negative charges. So if you look on that paper, it tells you 4 electron domains, 4 of those are bonding pairs, it's nonpolar. So any tetrahedral molecular geometry will always be nonpolar. Now the rest of them on that page you see are polar. So let's look at an example.
Casey Abrams, if you're in the building, would you please call 10029? Casey Abrams, please call 10029.
Sorry guys. If you want to determine if something's polar, then we're going to let's look at an example. Like H2O is a good example. Okay, H2O, for just time's sake. Water looks like that. That's the Lewis dot structure, or the Lewis structure for water. Now, I look at the electronegativity difference between oxygen and hydrogen. Oxygen is much more electronegative. So that means the dipole is going to be moving toward the oxygen. In this case, it's going to be moving toward the oxygen. Are these moving in totally opposite directions? No. They are moving toward the exact same spot. They're moving towards one another. Plus, oxygen has these 2 lone pairs on it as well. So there's all of these electrons that are trying to be surrounding oxygen. So nothing can really cancel out here. In this case, I call this polar. This overall is a polar molecule. On the top of this page is written for you, a molecule is nonpolar if the surrounding atoms are the same. So we saw that with CCl4. I had 4 different carbon and chlorine bonds, and we found that it was nonpolar. A molecule is polar if surrounding atoms are different. So a molecule can be polar if the surrounding atoms are different. Well, these surrounding atoms are different than my central atom here. There's another little key thing to that. It says a molecule is polar if the central atom has 1 or more lone pairs of electrons. This central atom has lone pairs. That automatically means these lone pairs can't be canceled out. The dipoles, we can cancel those out somehow with another dipole. But these extra electrons here, those extra electrons there, I can't cancel those out with anything. So anytime there is a lone pair on a central atom, that immediately makes the overall molecule polar. Okay, let's look at, this. So we've seen a few of these examples already. I tried to do some. I have HCl. That's a compound, hydrogen and chlorine. I know that chlorine is way more electronegative than hydrogen is, so I have a dipole here. So this means this is a polar compound. This is a polar molecule. And it's polar because I only have 1 dipole here and there's nothing else to cancel that dipole out. On this one, we did this one together. This is carbon tetrachloride. Carbon tetrachloride. There's a dipole, 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 dipole. They're all moving in opposite directions from one another. So it's like they're canceling those dipoles out. So this is nonpolar. There's another one here that's nonpolar, showing that fluorine is more electronegative than boron. So in this case, this would be symmetrical, and so this means that these are going to cancel out. It makes it nonpolar. In this last case, I have carbon with 3 hydrogens around it, and then 1 chlorine around it. So on this case, it was carbon with chlorine and 3 hydrogen. Well, do these have dipoles? They don't, because we already determined that that electronegativity difference between these two is smaller than that 0.4. So I don't have any dipoles here. But I do have a dipole between this carbon and this chlorine. And why do I have that dipole there? Because chlorine is way more electronegative than carbon is. So I need to add in my dipole. If this is the only partial charge that I have here, this is partial positive, this is partial negative. Here's my dipole. I have nothing else in this molecule to cancel out that dipole. So is this molecule going to be polar or is it going to be nonpolar? It's going to be polar. So polar is really just telling us that we have some type of partial charges present. Nonpolar is telling us that the electrons are shared equally amongst the entire molecule. Okay. Now let's go back to these slides. I have these examples, but I want to save those for class tomorrow. So we're going to look at just those examples in class tomorrow. The last few things, and I'll go through them very quickly. Intermolecular forces. Intermolecular forces are attractions between molecules. Now, this is saying an intermolecular force, with especially being an attraction between a molecule. It's not actually happening in the molecule. It's like saying that we have, here's a CO2 molecule, and here's a CO2 molecule. It's going to be the attraction somehow between these two molecules. That's what intermolecular forces are. It's the attraction between two molecules. It's not the attraction in between, like that carbon and oxygen. It's the attraction between two molecules, okay? So the differences in intermolecular forces are pretty much just the difference between attractive forces. There are three major types of intermolecular forces. So all I want you to know right now is intermolecular forces are attractions between molecules, and there are three types. There's hydrogen bonding, there's dipole-dipole, and then there's something called dispersion forces. The first one that was listed was hydrogen bonding. This is super simple, guys. Hydrogen bonding is an attraction that's formed between hydrogen and then a really, really, really electronegative atom. Specifically, it could bond with three different things. If we have hydrogen that's attracted to oxygen, nitrogen, or fluorine, that's where we can have some type of hydrogen bond. So hydrogen bonding occurs when hydrogen is attracted to oxygen, nitrogen, or fluorine. So let's look at this case here. I have three water molecules here. They are hydrogen. They are having an intermolecular attraction right now because I see here, this is hydrogen, this is oxygen, this is hydrogen. So this is just one molecule. So I don't have hydrogen bonding within this molecule because intermolecular forces are about attractions between other molecules. So here's a molecule, here's one, here's one. So the hydrogen on this atom, or this molecule, I'm sorry, this hydrogen atom on this molecule is attracted to the oxygen on this water molecule. So this right here is called the hydrogen bond. If I look at this one, this hydrogen is attracted to the oxygen on this water molecule. So this right here is the hydrogen bond. So it's not the bond here or here. It's the attraction between molecules. So this hydrogen is attracted to this oxygen. So that's my hydrogen bond. That's the attraction. This hydrogen is attracted to this oxygen. So this is my attraction here. This is my hydrogen bond. Okay? So hopefully that is a clear enough distinction. Our second type of intermolecular force is called a dipole-dipole interaction. You know that a dipole happens because there's a partial positive and a partial negative. Well, what happens if you have two really close molecules that have dipoles really close to one another? So like, for example, let's say we have HCl. That's a really good one. HCl, actually, let's use the partial positives and partial negatives. So this one has a partial positive, this one has a partial negative. This one has partial negative because it's more electronegative than hydrogen is. So hydrogen's partial positive, chlorine's partial negative. Well, let's say that it's really close to another another molecule just like itself, another hydrogen and chlorine bond. Well, hydrogen has a partial positive, chlorine has a partial negative. Look right here. I have a partial positive really close to a partial negative of a totally different compound. So right here is where we would say there's some type of dipole-dipole interaction, because this partial negative is really, really close to this partial positive of a totally different molecule. So that's dipole-dipole. I have one totally different molecule here that's attracted to another molecule because they are really close by opposite partial charges. So that's what I was trying to show here in this picture. I have a partial positive and a partial negative. That partial negative is going to be really close to another molecule, specifically the side that has a partial positive. Same thing down here. This partial negative wants to be close to a partial positive down here. So opposites want to attract. So whatever that partial negative charge is, it's going to try to find another partial positive charge of another molecule. So that's dipole-dipole interaction. Last one, guys, is called dispersion forces. Now, dispersion forces are caused by electron movement or electron motion. Electrons around one molecule can momentarily repel electrons by a nearby molecule, creating like some type of momentary charge difference. So think about this. Electrons, if I have two electrons that are surrounding or really close to one another, what are they going to do? Are they going to attract one another, or are they going to repel one another? They're going to repel one another. They have similar charges. So because they have similar charges, they're repelling one another, there can be some type of this very momentary charge difference. This can exist between polar molecules as well as nonpolar molecules. This is the weakest type of intermolecular force. It is the weakest type of intermolecular force. And all I want you to understand is that right now is that a dispersion force happens because electrons are momentarily repelling other electrons in a nearby molecule. So it's like these molecules are just repelling one another for just a moment. And think about why. Electrons are constantly moving, so those electrons can constantly repel other electrons because they're similarly charged. And similarly charged particles don't want to be next to one another. We are going to focus on these three intermolecular forces way more in depth once we get into the States of Matter chapter, which will be in second semester. But for right now, I at least just want to introduce them. Okay? Very finally, there's some properties of covalent compounds. Covalent compounds have relatively weak forces can break a covalent compound. So they have really low melting and boiling points. Think about why. Ionic compounds have really strong bonds because an attraction between a positive and a negative charge is really, really, really great. In a covalent compound, they're simply just sharing electrons. That bond is very weak. So if the bond is weak, it's not going to take a lot of heat or energy to melt or boil that compound. Most covalent compounds are relatively soft solids, so again, it's not going to take a lot to break or destroy that bond. And some covalent compounds can form network solids like diamonds. Diamond is a really pretty rare example of how a covalent compound can form a really nice, neat structure. Okay, we have finished our slides. I would like you to make sure that you bring this page back with you tomorrow. So make sure you bring this back tomorrow. And if you have any questions, post on the blog, or at least if you don't get a chance to post on the blog, write your questions down so we can go over those questions in class. And we'll do those three examples together in class as well tomorrow that's on these slides. If you have questions and they're dire and you absolutely can't wait for them to be answered, then post them on the blog and I will get to them as soon as I can. I'll see you guys tomorrow. My Macbeth people, good luck tonight, and I'm going to see it on Saturday, but good luck tonight. You're going to be awesome. For everybody else, have a really great night. Macbeth people, good luck. Or I'm sorry, break a leg. Break a leg.